Hey, Year 11. Thanks for coming along. I've only got a couple of people here at the minute, so I'm just going to give them a couple of minutes to see if I get any more, and then I'm going to crack on with the paper. So this is going to be the 2016 May. It's actually the 19th of May 2016's paper. We're going to see how far we can get. Interesting that the paper that I went through previously, which was the May 2015 paper, had 16 questions, whereas the 2016 only has 12. Obviously, the number of marks tallies. Hey, Hibber, thanks for coming. Nice to see you. Morning, Tom. Have you guys had a look at the document that I've created for you guys? You guys had a look at that yet? Just to see that you can put in your data. I know that, Tom, you sent me your percentage, so you can log your percentage on that previous paper or on this paper into that document. It just means I can keep track of it and I can kind of compare it to bits and pieces. Yeah, so if you can put your raw score and your percentage, that's great. If you can't, don't worry about it. It's not so much of a big deal. But I'm just trying to keep track of these now, bearing in mind that, I mean, we're meant to be going back in a week. So fingers crossed we'll be able to add to this before then, because I'm going to be setting you guys these papers now every lesson. And then looking at topics that people want me to have a look at. And I'm happy to go through any topics that people want. Okay, so I've got two of you. I think we're just going to crack on with paper. I want to make the webinar as short as possible, so let's share screen. Hey, Liz, nice to see you. Thanks for coming. Let's do that one. There we go. So I'm going to hide that so I don't press it. There we go. So this is the May 2016 iGCSE paper. This is the regional one, which is actually the one that you guys sit. So I'm just going to get straight on with it. I've drawn a line at question. Sir, where is the paper located? Which paper? What do you mean, which paper, and where is it located? Do you mean this sheet here? I shared it with you earlier today, Tom. And if you want to know where the exam paper is, I know that you've done it. If you go to the document, I hyperlinked it in and put paper 2 to be done. I did it in week 2 for Easter. There we go. Down here, 2016 May regional. Right. Okay, so surname, Duncan. And I never do this. Other names, Tobias. Oh, Tobias Mark, actually, but, you know, middle name. Anyway, sorry, first name should be Mr. Okay, geez, obviously your periodic table is there. Okay, thank you, no worries. Okay, so nice, easy start. Very similar to the 2015 paper, I thought. In the periodic table is shown on page 2. In the periodic table, which number increases from 3 to 10 in period 2? So that's the atomic number. An interesting question. Never kind of seen one like that. That's the atomic number. The reason being is atomic number. Nice one. Atomic number. That's just because it's increasing by 1 each time and it's moving across. If you look at the mass number, it's much higher already, even at the beginning. Lithium is number 7, for example, already, rather than being the atomic number 3. Oh, my pen seems to have suddenly decided to stop. Oh, it's back. Interesting. In the periodic table, which number increases from 9 to 226 in group 2? But there's only one number that can get that high, and that's the atomic mass number. So that's the atomic mass number. Interesting question. Never seen one like that before, but I can see what they're doing. They're just putting you in an awkward context. Here, so you're seeing in number 2 is it's increasing mass number as we go down the group. I know that the periodic table needs to be. I wonder if I can actually rotate that page. Can I do that? I have no idea if I can. I should be able to. Don't see why not. That one? Don't know. If I zoom out, If I zoom out, I wonder if I can rotate a single page. View. Color. Oh, what's that one there? Syncing. Nope, that's not what I want. Picture. Help. Does anyone know where the rotate button is? Do I just do it with my fingers? No, that's just trying to shrink it. That's not ideal. Meh, not that it really matters. Would have been nice. And then the other number from 3 to 10, from 3 to 10 on period 2, yeah, is that one. So it's moving across that way. So that one's, I've got to rotate that. I apologize for that. It's a bit of a nightmare effect since I can't rotate the image. Next, the atom of boron contains protons, neutrons, and electrons. Fill in the words with the correct one. The particle with the smallest mass, that's the electron. So that, of course, nice for me to mention that is quite an unusual question. Most of the time, they give you a table. Yeah, they'll give you subatomic particle, subatomic part, and then they give you mass. Yeah, and then they give you charge. This is usually what they do. And then they give you the pieces, proton, I'll get rid of that, proton, neutron, and electron. The mass, of course, is 1, 1, and then you are not allowed to put 0. That is not allowed. The word you remember is negligible, yeah? Or 1/1836, the year that Charles Darwin came back from the Beagle, if you really want to go that far. But I actually don't recommend it. I recommend the word negligible, even at A level. Next, charge of a proton is +1. You need to give the 1. Very common for students just to put plus. It's not enough. Yeah, you need +1. Neutron is 0 and electron is -1. So quite an unusual way that they've decided to orientate this question. Particle with the smallest mass is the electron. The particle with a negative charge, which is an electron as well. They're doing that deliberately to freak students out. They won't like the electron, won't like it. The two particles in the nucleus, we've got a proton and neutrons, of course. Nice and easy. In boron atoms, there are equal numbers of, in any atom. You don't actually need the word boron in this particular case. It's the same for all of them. They have equal numbers of protons and electrons. That's actually, I'm just suddenly realizing that I'm wanting to put the S on the end. Oh, look, protons, they want S. Yeah, on all of them. Because it's what's in the box. That's an interesting one. I wonder if they'd disallow it if you only put electron or neutron. That would be an interesting question there. That question, again, comes in all kinds of shapes and sizes. Yeah, boron atoms are equal numbers. Because what they like to do is they like to say, another version of that question is explain, I actually wrote the word letter Y. Explain why atoms are electrically neutral. Electrically neutral. And you're saying because, neutral. Neutral. And that's because they have equal numbers. The number of protons equals the number of electrons, and they're +1 and -1. So they have the equal numbers. Yeah, equal number. I'll actually put the little NO dot thing. Equal number of protons and electrons. Very common. The element boron has isotopes. These isotopes have different numbers of neutrons. We're okay with this. Nice, easy start to the paper. Nice sitting there at level 2, 3. Next, in this question, give your state symbols for the changes. Oh, okay. So water boils in a kettle. State symbol before change. State symbol after change. Yeah. Next, ethene is converted. That's a very clever question. Ethene, you've got to know that from organic. What a great question. Ethene is a gas. Now, students will say, how do you know that? Because you've collected it. When we did cracking, you collected that gas and tested it with bromine water. And polyethene, of course, all polymers are solids. Yep. Next, crystals of iodine sublime on heating. So that's going from a solid iodine, which is gray, to gaseous iodine, which is purple. Great questions all. Next, some marble chips are added to a solution of hydrochloric acid. Complete the equation with state symbols. Right, so limestone, again, one you've got to know. Oh, I wanted to put the brackets in then, don't need to. And that's a solid. Hydrochloric acid, of course, all acids are aqueous. That's the most common mistake. Lots of students will put L, but that's not correct. Acids are not liquids. Acids are aqueous, yeah? So bear that in mind. You do get, by the way, sulfuric acid is if you have pure concentrated sulfuric acid, it is actually a proper liquid. HCl is actually a gas, and you need to actually know that from the diffusion practical. Just to make you aware of that, you need to know that that guy there is a gas as standard, but then as an acid, it's aqueous. I'm just going to pull that off, nota bene. Yeah, HCl is actually a gas, but if it's a gas, you would call it hydrogen chloride. Yeah, you wouldn't call it an acid because it's not one. When you add it to water, you get HCl aqueous, and then the name changes, which is hydrochloric acid. Hydrochloric. Nice little change that. You need to know that because of the diffusion practical through the tube. We know that because that's aqueous, there's water present, so all chlorides are soluble. So that's going to become, all salts become aqueous, that becomes liquid, and CO2 becomes a gas. Nice and easy. Isn't that lovely, though? All state symbols represented in that particular equation. All of them. Most common mistake one is the hydrochloric acid. Most students will put liquid. Which state symbol is most often for the element in the periodic table at room temperature? Solid. That's a great question. Never seen that one before either. It's really nice just to mention. I'm just fiddling around with my laptop, by the way. I'm just flattening it out a bit. That's actually a lovely question. I think I mentioned that in the last bit. Do you know what I'm going to do? I'm actually going to add in a period. I think it'd be really useful for me to actually have a periodic table, which is actually the right way around. And I've got one on hand actually. So let's just insert that there, and I'll move that. So it's really nice. As I said, I think I mentioned this one in the previous webinar. There we go. So the periodic table, of course, is the most amazing piece of equipment ever. It pretty much dictates my entire life. But it's really nice just to say, there's the dividing line, starts at aluminium. I'll do that in a color. Yeah, there's the line. And we know that all of these guys here, all of them are solids, except for one. There is one exception, and that's mercury. Otherwise, every single one of them are solids. Yeah, that's a solid. That's the only L. Yeah, and then we get a whole load of other solids. I'm just going to shade those in yellow. Boron, a solid. Carbon, a solid. Silicon, a solid. Phosphorus, a solid. Sulfur, a solid. Arsenic, solid. Selenium, solid. Tellurium, solid. Iodine, solid. Astatine, solid, even though we never really talk about her because she's radioactive. She actually has a world record as being the rarest element on the Earth. So all of those are solids. There is one other liquid, and that's bromine. Bromine is the other liquid, and then everyone else is gases. I'll do the gases in red, I guess. Gas, 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 and gas. There we go. So most of them are solids. It's an amazing piece of kit. You can do so much with it. As I said, never seen that question before either. Rather clever that. They're checking. I mean, what are they actually testing there? They're testing that you've understood and you've had conversations about elements with your teacher. Like, that's a very bizarre question. I think it would be far more interesting if they actually asked you for the two liquids. That would be a fascinating one. I've never seen it. Mercury and bromine. And bromine is the most terrifying of all the elements. Absolutely lethal. Terrifying stuff. Okay, let's move on. The technique used to separate the mixture includes... Oh, what are we separating? Let's go back to the question. What are they separating? Techniques used in the separation of mixtures include... Okay. Oh, okay. Yeah. Okay. They're making you choose them. Oh, yeah, I quite like this question. Pure water from seawater. Fractional. Simple won't cut it, folks. Yeah, simple will not cut it. If you want pure anything, fractional is the only choice that you have. My pen keeps hiccuping. Wonder whether or not the battery's dying. I think I've got a spare battery somewhere. I might track it down in a minute. Next, ethanol from a mixture of ethanol and water. Oh, you could use simple distillation for that, but I'd probably use C again. Like, they're two liquids. And I don't think simple's not really a great choice. You could use simple, arguably. You wouldn't get a very good separation. You only get about 80% separation. So I still think I'm going to go for C. Calcium carbonate, that's a solid. We know that limestone is always a solid. Mixed in a mixture of calcium carbonate, that's going to be filtration. There's B, removing a solid. Yeah. Removing a solid from water, that's pretty easy. Right. Ooh, isn't that interesting? Hydrated copper sulfate from copper sulfate, aqueous. Oh, okay. Solid from aqueous again, folks. We're going to use filtration again. Oh, hang on a minute. That's really interesting. No. From copper sulfate, aqueous. Okay. That's much more tricky, that, because it sounds like that what that question there is doing is they're saying, I've got a beaker which has aqueous copper sulfate in it and crystals in it, which would be filtration. But that's not what they're saying. They're saying that you want to go from copper sulfate aqueous and produce hydrated salts. That's going to be crystallization. So that one's a bit more of a tricky one, that. Where's crystallization? A. Right, first one where I want to actually check a mark scheme. Wow, that didn't take very long, did it? I wanted to see the CC. That's all I want to see here, really. See if I can make this work. There we go. Let's try it. It's going to open like 3 of them now, isn't it? Okay. I want to check the CC bit. It also means I get to check the rest as well. I don't really need to check any of those. Oh, A, simple. It said pure water. I completely disagree. I would totally disagree with that, folks. That says pure water. Simple distillation would not be acceptable. I would argue an exam board with that. They're saying, no, I disagree. That is not the correct answer. I would fight Edexcel to tooth and nail for that. For them to say pure water, if you use simple distillation, you will not get, you would not get pure water. No way. It's wrong. Absolutely wrong. So they wanted DCBA. No, don't think so. Disagree. I will continue to disagree with that. Right, color, green. Isn't that fascinating, given fluorine is yellow? Fluorine's colorless in reality. If you actually had enough fluorine to see its color, you're about to die anyway. So it really doesn't really matter all that much. But fascinating. Iodine boiling point. Ooh, you're having to guess? Wow, never seen that before. I hope everyone realizes that that's really interesting. So hang on a minute. What does that go up by? That goes up by, that's like 190, like, so hang on a minute. One on my calculator, 188 minus 35. That's gone up by 153. And then the next one is gone up by what? Minus 35 minus 59. That's not, oh yes, that's gone up by minus, that's gone up by 94. My pen stopped again. I don't know. I wonder whether or not I'm pressing something. I think I'm pressing something with my hand. That's 94, folks. Yeah, 94 gap between those two. So what's the difference between those guys is give or take 60. So if that there is 60, it's really weird this. My pen keeps hiccuping. Guys, I'm just going to quickly grab I think I need a different battery. Backpack? Okay. It's not there. Sorry about that, folks. That's a nightmare. I don't know. I'll find out in a second. Right, so I have a new battery. Okay, so the difference between that one is like 60, isn't it? So I want to do 60 again. No, do I? Yeah, maybe. Yeah, maybe 60 again. It seems very reasonable. So 60 again would be 150, wouldn't it? No, hang on a minute. It's going to be 40. If I did 60 again, it'd be like 34. So 34 on top of that guy. That's not going to work, is it? It's going to be really close to that. It's really fascinating, isn't it? I kind of want to draw a graph. It's just really nasty. I want to draw a baby graph. God, if I was in an exam, fill in the table. Oh, talk about a waste of time. Yeah, we're going to plot these temperatures and get the next one. So we're going to have minus 188. Let's make it easy for ourselves. Let's go for minus 190 and then minus 30. Let's go all the way up to, let's go up to 200, shall we? And down to minus 200. That's really horrible. Minus 200. That there is going to be minus, it's going to be dead zero. Right in the middle is 0. Yeah. And then we're going to have minus 100. And then we're going to have 100 there. Fascinating. So we're going to have to go minus 190, which is like here. And then we're going to have to make this even. So fluorine, chlorine, bromine, iodine. It's just about kind of even. Yeah. So fluorine's like here. Fluorine is like there. Then chlorine is like minus 35, which is ridiculous. So that's minus 50. 35 is going to be about there. And then bromine is 59. 59 is like here. So that's like there. And there's my graph. So iodine, what a horrible thing to do to us. It's about 150. I'm going to put it about 150. How mean is that? That's really tough, that, folks. Predict the value for the boiling point of iodine. So hang on a second. It then says what color of the chlorine at room temperature. Oh, that's really weird. Green. Not actually read the question. I'm filling in the table when there isn't actually a mark for it. The trend in boiling points is similar trend to the melting points. Predict the value of the boiling point of iodine. I'm going to put 150. Want to check that immediately. Yeah. And then astatine is another element in group 7. Predict its color. Astatine, its color will be black. Yeah, iodine is gray. They get darker as you go down. There's iodine being gray. Astatine's going to be black. And its physical state is definitely going to be solid. Absolutely. But that's a prediction. Yeah, I want to check that straight. Well, I'm going to finish the question. The elements in group 7 have similar chemical properties because they have the same number of electrons. Hang on, electron shells, outer electrons, C, outer electrons. Yeah. The student wrote these statements. Okay, the 3 of the statements contain one incorrect word. Complete the incorrect word, correct word. Okay. How bizarre. The reactivity of the elements decreases down the group. That's correct for group 7. Yeah. The reactivity does increase down the group. Sorry, it decreases down the group. That's correct. Because the most reactive element in the universe is fluorine. The elements form ions with a single positive charge. That's now not correct. Yeah, we know that these are not positive. So the incorrect word is positive, and it should have been negative. The rest of it's all correct. Yeah, next one. The formula of astatine, the formula of an astatine molecule is At2. That is correct. Absolutely right. It is a molecule. Yeah. The equation for the reaction between chlorine and potassium bromide solution is... The equation for the reaction between chlorine and potassium bromide... there's the mistake. That's clever. Yeah, it should have been potassium's the wrong word. That's really clever. Potassium should have been sodium. I think that's fascinating. I wonder if the next one's going to be the same. In the reaction between bromine and potassium iodide, bromine acts as a reducing agent. Oh, blimey. Right, that's, by the way, first level 8. There's a love 8 right there, folks. Yeah, love 8, 9, really. So we've got bromine reacting with Ki to form I2 and KBr. Balance it, can't not. Right, this starts with an oxidation state, a charge of 0 because it's an element. Iodide starts off with a charge of -1 and it's becoming 0. So it is being oxidized. So that there is an oxidizing agent. That's really hard, folks. It's level 8, 9. Yeah, it really is. So it's not a reducing agent. It's an oxidizing agent. Fascinating. So the wrong word is reducing. And the correct word is oxidizing. Now, if students are wondering how I'm getting to that decision, which I have no doubt there'll be students watching this who just go, what just happened? So group 7 ties into redox. And you guys studied redox at GCSE very briefly, not a huge amount, but you studied it for electrolysis. And it also ties in with group 7. So the first thing we need to talk about is what's called oxidation states. Now, oxidation states, the word oxidation is just is a posher word for charge state. Yeah. So this here is what charge is on each of the atoms in a compound. So, for example, if we have something like hydrogen gas as an element, yeah, the atoms of hydrogen have an oxidation state, a charge. I'm actually going to say it. I'll put oxy state, but then I'll put / charge of 0. And that's actually by definition. We realize that if they're not bound to anybody, nobody's gained or lost electrons. Therefore, it must be 0 because the number of protons balances the number of electrons. That's what we know. Yeah, if it's not in a compound, no electrons have been lost or gained. So I have a charge of 0. Once you then put it into a compound, something like water, we all know that the oxygen here, the charge on hydrogen is +1, and the charge on oxygen is -2. We all know this. It comes from the periodic table in this setting. It doesn't when you get to A level. Well, it kind of does, but it doesn't. But at GCSE, it's just coming from the table. We know that if you go to the periodic table, that hydrogen always becomes +1 and oxygen always becomes -2 because they're in their following groups. Yeah, hydrogen stands alone. Hydrogen's +1. It should live here. Yeah, that's where it should be living, in the +1 group. And then oxygen is in group 6, which is -2. It's going to gain 2 electrons. So now I need to do the redox bit, because We then go, well, hang on a minute. So let's now look at the equation of bromine. Right, so bromine has a charge state. I'm going to put oxy state. I'm not actually going to write charge state, though. A charge state of 0, because it's an element by definition. It is not in a compound, therefore has lost or gained no electrons. I'm going to react it with potassium iodide. Now, K, potassium is in a +1 because it's lost 1 electron to the iodine, and the iodine has become iodide and is in a -1. I hope everyone agrees with that. Right, during this reaction, during the reaction between these two, electrons are swapped. I become KBr. Right, so what's happened? Potassium hasn't changed. Potassium is still +1 because it's in a compound. And bromine has become bromide at -1. So what's happened from here to here? It has gained an electron. Yeah, gain 1 E-. It's gained 1 because it's become minus. Yeah, it's gone from 0 to -1. It's gaining a negative electron. And what else have I then made? I've also made iodine. And the iodine, I'm going to balance them. The iodide has become iodine and has gone from a -1 to 0. Well, what's happened there? Oh, it's lost an electron. Yeah, E- lost, and this is E- gained. Yeah, and we remember oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. So what's happening? So number 1, who is losing electrons? Iodide to iodine. So that is going through oxidation, and bromine is making him do it. So he is the oxidizing agent. I know that you're thinking, wow, that's really complicated. It gets easier. I swear to God, it gets easier the more you do it. But yes, that is level 8-9 for that very reason. That's tough, that. Next, right. Good old chromatography, we know this. Explain why it is important for the solvent level to be below the spots. Because otherwise, the inks will go straight, it will dissolve into the water and not run up the page. Yeah? Ink will dissolve into solvent, might not be water, into solvent and not move up page. Not move up page. I want to see what they wanted for that. That's interesting. I haven't seen them ask that. They kind of drop out. They drop off the paper, and I just feel like they want specific words there. Yeah, ink will dissolve into the solvent and not move up the page. That's what I would say. Let's see the mark scheme. Still disagree with that. They're absolutely wrong. C, green. Oh, what did I put? I put 150. Yes, right in the middle of their range. I like it. Color, darker gray or black, solid. I like it. Positive, negative, potassium reducing agent, oxidizing agent. I like it. To prevent them from dissolving, so mixing with, except substance, pigments, dyes, or spots, ignore references to diffusion, references to spots, smudging, or running, except spots would wash away. Ignore water for solvent. Okay, so them dissolving into the solvent. So I got it right. That's okay then. State 2 potential problems that are prevented by fitting the tank with a lid. 2. Well, number 1 is you're going to prevent the solvent. Prevent solvent from evaporating. What would the next one be? Evaporating. Prevent it. Is that how I spell it? I feel like it's not. Evaporating. What would be the other one? State 2 potential problems that are prevented by fitting the tank with a lid. 2. Prevent the solvent from evaporating. Preventing water getting in. The student investigated the pigment found in some vegetables and fruits. She obtained some colored vegetable oil, yada, yada, yada. She places the spots of the extracts. Yeah, a teacher provides the solvent containing volatile flammable. Right, volatile, there's the answer. Yeah, volatile means to turn into a gas. So the lid is to prevent it from evaporating. And also, it's flammable. So we're also going to say, prevent it from evaporating. I don't know what the second one is. Two potential problems. Prevent solvent from evaporating. Prevent flammable gases escaping. Even though it's the same thing. Flammable gases escaping. I feel like the answer's in the question. Escaping. If it was toxic, it would make more sense. I guess that makes sense. Flammable gases. Check the mark scheme. Loss of solvent, risk of fire. Fumes, maybe for toxic or poisonous. Yeah. Ignore harmful or dangerous. Ignore it is flammable only. Accept water as a solvent. Yeah. Risk of fire. Reference to substance entering the tank. Yeah, fair enough. Okay. Fine. The diagram shows the chromatogram at the end of the experiment. Okay, place a cross in 3 boxes to indicate your choices. Which of the 3 statements are supported by the chromatogram? Chlorophyll, P2. Chlorophyll, just checking that. Yep, chlorophyll is not present in carrots. This is correct. Yay. Place a cross. Oh, can you explain how toxic fumes is produced? Because I put it as one of my answers and got the mark for it. How toxic fumes is produced. Tom, that's a really good, so where was, oh, anyway, right. That's a really good question. So Tom, what they're saying is that I think you'd probably agree that I got a bit stumped by the question. I was like, oh, so hang on a minute. I don't know enough about it. So I went back to the question and I saw these 2 words and I kind of felt like they were giving me the answer. Well, if this is an organic compound, yeah, and I mean, I know a lot about organic compounds and lots of them are very toxic. And so they allowed you to make an assumption that not only are these organic compounds, like there's not many organic solvents you can drink. Ethanol would be one of them, I guess. But even that's kind of toxic as well. So they're allowing you to use your own knowledge of this, Tom. So absolutely correct for you to say that they're going to produce toxic fumes. Prevent toxic fumes from escaping. Yeah. Doesn't mine look like hammable? I've got hammable gases. Gases that are in ham. Sorry. But yes, Tom, it's a good answer. Yeah. They're allowing you to use your own knowledge there. Did you notice, by the way, that I put a tick into my box and I realized that that's not allowed? That is correct. They want me to put a cross there. So let's go back to that. There we go. And then beta-carotene is present in beta-carotene is P1, is present in carrots, but not in tomatoes. So beta-carotene is there, is present in carrots, V1, and tomatoes, V2. So that's not correct. Both beta-carotene and lycopene are present in sweet potatoes. So I'm going to go sweet potatoes are V3. And I'm going to go lycoproteins is there, or lycopene. Lycopene, yes. And what was the other one? Beta-carotene. Beta-carotene, P1. Yep, that's both there, so that one is correct. Next, lycopene is present in tomatoes, but not carrots. Lycopene, tomatoes, carrots. That's not correct. Both carrots and tomatoes contain a pigment other than these 3. What did they say? Both carrots and tomatoes. Right, carrots, V1. They've got 1 there, which doesn't tie in. And then, was it tomatoes? And then tomatoes, which are V2. There you go. Nobody identified. So that one is also correct. I like it. One of the pigments present, it appears at a very faint spot of 1.3 centimeters cubed above the star line, calculated its RF value. Right, that's fascinating. So have they given us the end value? No, they haven't, but they've given us the equation. So distance traveled by the pigment is 1.3. Let's color code this, shall we? So distance traveled by pigment is there. So RF is 1.3 over distance traveled by the solvent. Right. So at this point, I'm going to have to get my ruler out. And I'm going to have to measure that with my ruler. Yeah, very, very carefully. They're going to give us no leeway here, folks. And I can't do that because it's on my tablet. Can't do it. Oh, ruler? I don't know if it's going to let me do this. It doesn't seem to have any numbers on it. I really hoped it would. And if I zoom in, you see, it doesn't actually change the ruler, which is a bit frustrating. Oh, it does. It does. It does. I love the fact that it goes on forever. Right, okay. It actually changes it. That's amazing. Okay. So let's take that as 0. Oh, I didn't know I could do this. So you can see that we're going to read this bit here as 0. That line there is 0. And I've got 1 centimeter, 2, 3, 4, 5, 6, 7, 3. 7.3 centimeters. I'll turn that off now. 7.3 over 7.3. And I hate the fact that it shouldn't be in centimeters, folks. It should be in millimeters, just so you know. Over 7. Oh, 1.3 over 7.3. 1.3 over 7.3 gives me 0.178. How many decimal places do they want this? I'm going to put that. I'll also want to check that mark scheme straight away for that one. Oh, put it on the line. 0.178. I think it's meant to be to 2 decimal places, but suggest a reason why there was a spot on the starting line in the chromatogram for sweet potato. There was a substance which was insoluble. That one there will have been insoluble. There is a pigment. There is an insoluble pigment in sweet potatoes. Sweet potato, sweet potatoes. Right, want to mark that straight away, folks. Definitely. ACE, I'm happy. Over 6, made a mistake. That's fascinating. What have I done? Look at that. What did I do, guys? What did I do to get that wrong? I'm wondering whether or not it's my ruler. I don't know what I did. It's not giving me any, it's not giving me any numbers on the ruler. I feel like the ruler's let me down, folks. I feel like that's what's happened here. Yeah, anyway, my ruler let me down. Never mind. I would have got it right if I'd had a ruler. I didn't check the insoluble. There is a substance that does not dissolve or is insoluble. I like it. Okay, let's move on. Right. How are we doing for time? Hydrogen chloride is formed in the reaction between hydrogen and chlorine. Name this type of reaction. Ooh. Oh, no. Type of bonding. Sorry. Apologize. Covalent. This is simple covalent bonding. I'm still getting some hiccups. So, by the way, you don't need the word simple, just so you know. Simple covalent bonding. All of it is. That's simple covalent, that's simple covalent, that's simple covalent. They all are. Yep, I like it. The bond in a hydrogen molecule is strong. Explain why the boiling point of hydrogen is so low. Great question. Susan Boyle sings Nelly the Elephant. Structure, hydrogen. Hydrogen is a covalent Structure. Covalent structure. Bonds, there are weak. I should do it properly. There are weak Tom, you spelling this all out properly for me? Intermolecular forces, WIMPs, between molecules. Strength, that's what the next S stands for. These forces are very weak. The number of them, there are very few. Few forces. Energy to break is low. Energy to break. Yeah, I did say. Good job, Tom. Well done. Energy to break is low. I like it. Great job. Boom. Stick with that. Explain how the two atoms in a chlorine molecule are held together. Right, okay, they want us to explain a covalent bond. So, there is a shared pair of electrons, 1 mark, shared pair of electrons between Cl atoms. I shouldn't do that. I wouldn't do that in a real exam. I'd write the word chlorine, just so you know. Between chlorine atoms, there is a strong electrostatic. This is the one that everyone will miss. There is a strong electrostatic attraction between shared pairs, pair of electrons. Shouldn't do that too. Electrons and the nucleus of each atom. I'm now going to draw a picture. So I've got nucleus, dot and cross, make that clearer. I'm going to shrink my pen down. Yeah, and then there's attraction between those and that and that. So what's happening? I like that. Draw a dot and cross diagram for the molecule of hydrogen chloride. I like it. So what we're gonna do is we're gonna turn HCl into this. Step 1, turn it into that picture, have the sticks. We remember that hydrogen makes 1 bond and all group 7s make 1 bond. We're then gonna turn it into this picture. In fact, we can go into this picture. Right, there's H, there's each atom has a circle. There is 1 bond in the gap, therefore 1 shared pair. And now make everyone add up to 8 except hydrogen. So chlorine needs to add up to 8, and I'm done. Nice and finished. Next, hydrogen chloride gas dissolves in water to form there's hydrochloric acid. Hydrogen dissolves in methyl, gas dissolves in methyl benzene to form solution B. A teacher adds a piece of magnesium ribbon to each. Explain what she observes in the two. How fascinating. Now, guys, I have taught you this in acid base. Acids are only acids when in water. Methyl benzene is not water. So we're going to say, so just to put this into a picture, so here's water, here's methyl benzene. Yeah, we'll do the water in blue, and we'll do the methyl benzene in red. I don't know why it's just gone and done that. How fascinating. Bizarre, isn't it? There we go. Methyl benzene in red. So here's what now happens. You put HCl into water. This is water. And what we know happens is it dissociates, it ionizes. And that is what makes an acid an acid. Yeah? So in water, it ionizes to form H+ ions. So it says, a piece of magnesium ribbon is added to each. Explain why she observes efflorescence in A but not in B. Right. In A, the HCl molecules dissociate. You can say dissociate or ionize, whichever one you want. Dissociate to form H plus and Cl minus. H plus reacts with magnesium. To form hydrogen gas. To form H2 gas. Right, in B, the HCl molecules do not ionize. Do you see how do not ionize? I've changed my word just to show you both being used in the same setting, folks. Yeah, molecules do not ionize, so no reaction. So no reaction with magnesium. Clever question with MG. How fascinating. And what does it look like in an image? If I put HCl into methyl benzene, it just remains HCl. Yeah, so no H pluses are formed. Yeah, I'll just leave one. There you go. So it starts off that, but in the water, it splits up. That's what we know happens. Yeah, in water, in methyl benzene, it's easier for me to do this than to write methyl benzene. That's methyl benzene. It stays HCl, doesn't ionize. I want to see the mark scheme. Okay, let's mark this question because what a fascinating question it's been. I got that number wrong because my ruler didn't work. Right, simple, let's have a look. Covalent, ignore reference to polar bonding and electron sharing. Okay, that's fine. It's interesting that they don't say ignore simple. It's fine. Weak forces between molecules, therefore little energy required to overcome or separate. Ignore more easily to break. Ignore reference or implication to breaking up. Yeah, that's fine. Next, strong attraction between shared pair of electrons and nuclei of both atoms. I like it. Bonding, shared pair of electrons, strong attraction to nuclei. I like it. Dot and cross. Effervescence due to hydrogen. Wow, that was lucky that I gave it, wasn't it? A is acidic, contains H plus, contains hydrochloric acid, except hydrogen does not ionize, stroke dissociate. Contains H plus. I like it, and I think we said all of that stuff, didn't we? There we go. H plus reactions. I like it. Full marks there. Does anyone have any questions so far? We're now at 52 minutes, and we're halfway through the paper. What I'm going to do is I'm going to complete the hour. I've got 7 minutes. I'm going to do question 7. Seems quite short, but it's a nice bit of organic. And then I'm going to end it at that point. Right, the table shows. So you should be able to name every single one of these, folks. Yeah, all of them. So what I'd like you to do, please, Year 11, if you haven't already done so, can you pause the video now and name all 6 compounds, please? Fab. So the first one is methane. Tick it if you got it right. Next one is prop-1-ene. If you really want to go to the number extent, that's what I'd expect at A-level. By the way, you're allowed to just call it propene if you like. The next one is propane. The next one is butane. The next one is bute, and I'd expect, Year 11, I would expect you to be giving this number. But-2-ene. At GCSE, they would allow just butene. And the last one is cyclobutane. There you go, folks. Right. Explain why all of these compounds are described as hydrocarbons. Because they are all made from hydrogen and carbon. Hydrogen and carbon. And you must say this word. Only. Yeah. They are all compounds made of hydrogen and carbon only. Why are B and E? I do want to put all made from hydrogen and carbon. All compounds. I'm going to add that word. I feel like there's a mark in there I want to get. All compounds made from hydrogen and carbon only. Why are B and E described as unsaturated? B and E contain carbon. B and E contain carbon. No, see what I've done there? I shouldn't do that. It's bad. Shouldn't do it. Carbon, double bonds. Love it. Gotta say carbon, folks. I know it's a pain, but you do. Which letter represents the first member of the homologous series of alkanes? And that's going to be A. That's methane, right? Yeah, methane is numero uno of the alkane homologous series. Which letters represent compounds which have an empirical formula of that one? That's CnH2n. That's alkenes. So that's B and E. Oh, I'm about to lose it because there's another one as well. There's another one that has it, guys. Cyclose. It's F. That's a trap. That's a trap. That raises the level from a level like 5, 6 to a level 7, 8, that, folks. Yeah, because most people see that and they go, oh, alkene. Yeah, that's most of the time what they do because they've been given the general formula. What they forget is that alkenes can also, they also have isomers. If I take propene, which is C3H6, and its empirical is CH2, yeah, shouldn't say or, no, wrong word, it would just be emp, yeah, I can also, with that formula, I can also draw this, not the same family, totally different family, that there is cyclopropane. So the cycloanes also have the same empirical formula. That's a trap, that, folks. Takes it up the level much higher. Compound F have the same general formula as an alkene. Why does F not decolorize bromine water? It does not contain carbon-carbon double bonds. Carbon double bond. Carbon-carbon double bond, so won't react with bromine water, Br2 water. I wouldn't do that in an exam. I'd write bromine. I just realized I've got 3 minutes till the hour. One of the compounds in the, good old empirical formula, fantastic. Carbon, hydrogen, bromine, 22.2%, 3.7%, 74.1%. Steps: percent to mass, mass to moles, divide by the smallest to find the ratio. Right, percent to mass, mass to moles. Remember, number of moles is grams over rams. Well, I'm counting atoms. Oh, bromine. What's the weight of Br? Oh, 80, I believe. I'll check that on the periodic table in a second. So I'll actually know from the numbers. 22.2 divided by 12 gives me 1.85. 3.7 divided by 1 is 3.7. And then 74.1 divided by 80 gives me 0.926. It's the correct number. It's the correct number because it's a ratio of that one there. Isn't that clever? Yeah, I did say I'd know it from those answers. Right, divide them all by the smallest. 0.926, 0.926, 0.926. So that gives me 1, 2, and what's, well, I'm just going to do, 3.7 divided by 0.926 gives me 4. The answer is actually 3.995, but I'd actually put 4 in the answer. So the final thing is going to be empirical, is going to be C2H4Br1. We're done. Next. The actual formula weighs 216. Right, well, how much does the empirical weigh? Well, I've got empirical C2H4Br is 12 times 2 plus 1 times 4 plus 80. Gives me 12 times 2 plus 4 plus 80. Gives me 12 plus 12 plus 4 plus 80. My calculator went mad. 108 makes total sense. Look at those two numbers. So times it by 2. So final number. Timesing it by 2 gives 116. So C4H8Br2. And I'm done. Let's check my answers. They all contain hydrogen carbon only. 1 mark. Double bond. I like it. A, B, and F. There we go. Has no, therefore saturated. Run my numbers, and there's my numbers. I like it. 2, 4, 1. Cool, that brings us to the end of this webinar, folks. We've done exactly 1 hour, which is really nice. And we are up to question number 8. So we're more than halfway through, which is great. Kind of good timing there as well. So I'm going to say end of part 1. Oh, do it in pen. End of part 1. I will do the other one tomorrow. We'll finish it off. Right. Let's bring my laptop back to normal. See if I can see you guys. I know there's only 3 people watching now, but that's okay. At least they can always watch it back. Right. Okay, folks. I'm going to love you and leave you for the rest of the day. Oh, Laura. So nice to see you. Was it useful, Laura? Did you see the empirical? Did that all make sense? Yeah, I think we finished empirical, didn't we, on our last thing? We just need to do water crystallization on year 10s. Thanks, Tom. You are so very welcome, Tom. Can I just say that it genuinely makes me happy seeing you at these webinars, like week on week, lesson on lesson. Thank you so much, Tom. I appreciate it so much. You are doing so great. Keep up the hard work. Oh, hey, Winkit. What time is our webinar? 2 o'clock, Winkit, for the A-level paper 1 run through. Tom, if you're interested in seeing a paper 1 A-level paper, come along. Guys, have a great rest of your day. It's been awesome to see you guys. See you soon.